Welcome to Sri Krishna Educational Channel. Please like, share and subscribe my channel. In this video I am going to explain about ethers and its properties from class 12th chemistry chapter number 11, that is alcohols, phenols and ethers. So first let me discuss the nomenclature of ethers. So in the case of the nomenclature, we can discuss both the IUPAC name as well as the common name. So first if we see the ether functional group simply which is ROR functional group. So in this case, with respect to this oxygen, with the both sides if it is having the methyl group, so its IUPAC name is methoxymethane. It would become as alkoxyalkane. So it is a methoxymethane, whereas the common name is dimethyl ether. So it is comes under the symmetrical ether. Whereas if you see the next one, that is CH3O CH2CH3. So this case it would be, this is methoxyethane. Methoxyethane is the IUPAC name, whereas common name is ethyl methyl ether is the common name. It is comes under the unsymmetrical ether because with respect to oxygen, one side which is having the methyl group, other side which is having the ethyl group. So it is a unsymmetrical ether. Next one, CH3CH2O CH2CH3. So it is known as ethoxyethane is the IUPAC name, and the common name is diethyl ether. It is also comes under the symmetrical ether. Next, OCH3 group which is present on the benzene ring. So this is known as methoxybenzene, or also known as the anisole. This is the IUPAC name. The common name is methyl phenyl ether. It is also considered as the anisole. So it is comes under the unsymmetrical ether. Next, when the ethoxy group present on the benzene ring, so that is known as ethoxybenzene is the IUPAC name, and the common name is ethyl phenyl ether. So it is also known as phenitol. This is the common name. It is also comes under the unsymmetrical ether. Now the next one, with respect to the oxygen, both sides which is having the phenyl group, that is known as phenoxybenzene is the IUPAC name, and the common name is diphenyl ether is the common name. So it is a symmetrical ether. Another compound, that is CH2 double bond CH2O CH3. So this is known as 3-methoxy-prop-1-ene. So this is the IUPAC name. Common name is methyl prophenyl ether is the IUPAC name. It is also unsymmetrical ether. Another compound is CH triple bond CH2O CH3. So this is 3-methoxy-prop-1-ene is the IUPAC name. The common name is methyl prophenyl ether, the IUPAC name. It is also unsymmetrical ether. And this compound you can see, it is CH2 double bond CHO CH double bond CH2. See, it is known as ethene oxyethene. In the case of the common name is divinyl ether. So it is a symmetrical ether. The last compound which is CH3 CH2O CH3 CH3. So it is known as 2-ethoxypropane. Second position, this ethoxy group is present to the propane, and the common name is ethyl isopropyl ether is the common name. It is also unsymmetrical ether. So this is about the nomenclature of ethers, and these are the mainly two kinds. One is symmetrical and other one is the unsymmetrical ethers. Next, the electronic structure if we see, so it is having the carbon and oxygen. Between that there is a single bond is present. That single bond is a sigma bond, and the carbon and oxygen, so those will undergo sp3 hybridization. So the bond angle in the case of this, which is 111.7, the bond angle which is more because due to the steric hindrance as well as the lone pair repulsions. Due to these two reasons, the bond angle which is more than that of the sp3 hybridization. This is the electronic structure of the ether. Next, the preparation methods of ether. So in the preparation method, it can be prepared by the dehydration of alcohols. When the alcohols which undergoes the dehydration in presence of the sulfuric acid, concentrated sulfuric acid, so it can be acts as a dehydrating agent at the particular temperature, okay, that is 443 Kelvin. So that case it will give the dehydration, whereas at 430 Kelvin, so it can gives the ether. So when the ethanol, which is treating with the excess of concentrated sulfuric acid at 443 Kelvin, so the dehydration can be takes place, it forms the ethene, whereas the same ethanol 2 moles which is treating with the concentrated sulfuric acid at 413 Kelvin, 413 Kelvin, so that case it gives the ethoxyethane. It is also known as diethyl ether. Okay, the mechanism of this conversion of ethanol to ethoxyethane, which is important. So in this case, first when the ethanol which is treating with the acid containing the proton, so that case it forms the oxonium ion of the ethanol. So it forms this oxygen containing pair of electrons which can be attacked on this H plus. So it can be forms the oxonium ion. So oxygen gets the positive charge. Next, the another ethanol molecule which is having the oxygen having the pair of electron which can be attacks on the H2O consisting the this oxonium ion. So that case it can be lose this water molecule and forms the bond between this the ethanol molecule and this ethyl group, and the oxygen again having the positive charge and the water molecule which is removed out. And the last step, that is deprotonation. So in this case the bond between the oxygen and the hydrogen which can be moved towards oxygen, so that case the H plus can be removed out, it forms a ethoxyethane. Ethoxyethane can be obtained. So this is the 3-step mechanism. First step is protonation, second step is the propagation, and third step is the deprotonation. So this is the mechanism of conversion of ethanol to ethoxyethane. Next, by the Williamson synthesis also we can obtain the ethers. So in this case, when the sodium alkoxides which are treating with the alkyl halides, so that case we can get the ethers can be obtained. So here this reaction which is carried out according to bimolecular nucleophilic substitution reaction, that is SN2 mechanism, this reaction which can be carried out. So first the sodium alkoxide which is treating with the alkyl halide, it forms ether, and in addition to that it can also forms the sodium halide. If the sodium alkoxide consisting the alkyl group and the alkyl halide consisting the alkyl group, those are same, that case it forms the symmetrical ether. When those are different, that case it forms the unsymmetrical ether. The alkyl group, it is a secondary or tertiary alkyl group, okay, in the sodium alkoxide, then the ether which is also synthesized by this reaction. So if it is suppose the tertiary sodium alkoxide, tertiary isobutyl alkoxide which is treating with the methyl halide, so it can be obtained the methoxy tertiary butane, this can be obtained. So in addition to that sodium bromide can be obtained. Okay, whereas if you are taking the tertiary butyl halide and the methyl sodium alkoxide, so in this case the ether cannot be obtained. So that case the dehydrohalogenation can be takes place in the case of this tertiary alkyl halide. So the ether cannot be obtained, and in addition to that it can be found the methanol. So this is a slight variation when the tertiary butyl alkoxide is present. So that case tertiary butyl oxide is present, so that case it forms the ether. Whereas when the tertiary butyl halide which is there, so that case it do not form the ether, which leads to formation of dehydrohalogenation, hydrogen as well as the halogen which can be leaved from this the tertiary butyl group. As a result, it forms the unsaturated compound. So this is the Williamson synthesis. By the Williamson synthesis also we can obtain the ethers. So in case of the aromatic alcohols, that is phenol. Okay, when the phenol which is treating with the sodium hydroxide, it forms sodium phenoxide. Now the sodium phenoxide which is treating with the alkyl halide, So that case it forms the ether. Ether can be obtained. That is alkoxybenzene can be obtained. In addition to that, sodium halide is formed. So this is also the aromatic ethers also can be obtained by the process of Williamson synthesis. Like the physical properties. So in the case of the physical properties, okay, first the ethers consisting the carbon and oxygen bond. So that is in the ethers which is a polar in nature. So due to the polar nature, okay, the dipole moment it is produce certain amount of the dipole moment, but the polarity in the case of the ethers which is less when comparing with the alcohols, okay, and other compounds. So this due to this the boiling point difference also observed in comparing with respect to the alcohols and ethers. In the case of the alcohols, which is presence of the hydrogen bonding, but ethers which is having present the hydrogen bonding, okay, which is very slightly present in the case of the hydrogen bonding. So here the comparison with respect to the alkanes, ethers and alcohols, if you see the alkanes which is having the boiling point 309, that is n-pentane, if you see its molecular mass, and ethoxyethane molecular mass and butane 1-ol molecular mass almost similar. So the boiling point of n-pentane which is 309.1 Kelvin, the boiling point of ethoxyethane is 307.6 Kelvin, whereas the boiling point of butane 1-ol is 390. So if we compare these, here the alcohol has more boiling point than that of these alkanes as well as the ethers. Okay, the alkanes and ethers, those are almost similar boiling point. So that is due to the ethers which is the absence of the hydrogen bonding, similar like the alkanes. The miscibility of ethers, okay, with water, which resembles those of the alcohols, okay, the same molecular, like the similar molecular mass, okay, both the ethoxyethane and butanol, those are miscible in the almost to same extent, that is 7.5 as well as the 9 gram per 100 ml water, while pentane, we consider the pentane, okay, which is immiscible in the case of water, okay, that is due to more hydrophobic nature. So that is this is due to here the pentane, okay, it's just okay, do not form any kind of hydrogen bonding with respect to the water molecule, but the alcohol, the oxygen and the ether which is also consisting the oxygen, it forms the hydrogen bond with the water molecules. Okay, due to this hydrogen bonding with the water molecules, okay, it can be, okay, soluble in the case of the water, okay, like similar like alcohols. It can be formed the hydrogen bonding with the water molecule, but within the ethers the hydrogen bonding can be absent. Okay, this is the physical properties of ethers. Next one is the chemical properties. Here in case of the chemical properties, there is a two kind of chemical properties can be observed. That is one is the involve of cleavage of CO bond. Second one is the electrophilic substitution reactions. Okay, that is take place in the case of the aromatic ring. So in this first one is the reactions which are involving by the cleavage of CO bond, carbon oxygen bond. So here when the ROR, okay, that is ether which is treating with the hydrogen halide, so it forms alkyl halide plus alcohol can be obtained. Now the alcohol which is further treating with the hydrogen halide, again we can obtain the alkyl halide and water. So these are the products can be obtained. When the ether is treating with the hydrogen halide, it forms the alkyl halide and alcohol. Now the alcohol again treating with the hydrogen halide, that case we can obtain the alkyl halide and water. So these are the products can be obtained. Similarly, when the aromatic ether, that is alkoxybenzene. So when the alkoxybenzene which is treating with the hydrogen halide, so that case we can obtain the phenol, okay, and in addition to that the alkyl halide can be obtained. Phenol and alkyl halide can be obtained. So in the case of the symmetrical and unsymmetrical ethers, okay, also we can obtain the same kind of products. Okay, when we are taking the unsymmetrical ether, so which is treating with the hydrogen halide, okay, we can obtain the alkyl halide plus the alcohol. Alkyl halide plus alcohol halide is obtained. Now in this case, the hydrogen halides, the reactivity, if you see, the hydrogen iodide which is more reactive than the hydrogen bromide than hydrogen chloride. So this is due to the more bond length between the hydrogen iodide rather than the hydrogen bromide and chloride. So this is the order of reactivity towards the ethers among the hydrogen halides. That is, hydrogen iodide is more reactive than hydrogen bromide than hydrogen chloride. So the mechanism of this step, if you see, so in this case when the ether which is treating with the hydrogen iodide, so that case the ether consisting the oxygen has a two pair of electrons. These two pair of electrons, one of the pair which is attacking on the hydrogen iodide hydrogen, so that case it forms the oxygen ion of the particular ether. In addition to that, iodide ion is obtained. Now the iodide ion which can be acts as a nucleophile, which can be attacks on the alkyl group of this oxygen ion of the ether. So that case it forms a transition state. Okay, next the transition state which can be further decomposed here and gives the alkyl iodide, methyl iodide plus ethanol. Okay, this can be obtained. So now this is undergoes according to SN2 mechanism. Okay, bimolecular nucleophilic substitution reaction. In that sequence, so the reaction can be carried out. Next, third step, this ethanol which is treating with the hydrogen iodide, it forms the again oxygen ion and iodide ion. Now this iodide ion again which can be attack on this the carbon, so that case which lose the water molecule and we can obtain the alkyl iodide. So this is the three-step mechanism. It can be follows according to SN2 pathway. The reaction can be carried out by molecular nucleophilic substitution reaction. Next, reaction with the dilute acids. When the ethers which are treating with the dilute sulfuric acid which undergoes hydrolysis, okay, followed by the heating at a particular pressure, so that case it gives the ethanol. 2 moles of ethanol can be obtained. The ethers which are treating with the hydrogen bromides, so followed by the heating we can obtain the bromoalkanes. Here we are taking the ethoxyethane, then we can obtain bromoethane can be obtained. In addition to that, water molecule also formed. Okay, the mechanism of this reaction, if you see, when the tertiary butyl methoxy tertiary butane which is treating with the hydrogen iodide, so that case which can be forms methanol plus tertiary butyl iodide can be obtained. So now this tertiary methoxy tertiary butyl group butane which is treating with the H plus, so it can be forms the oxygen contain the pair of electrons which can be donated to the H plus and initially forms the carbocation. The cleavage can be takes place here, that forms the carbocation and methanol is obtained. Okay, the carbocation which is consisting the tertiary carbocation is obtained. The tertiary carbocation is the more stable and this is reaction is a slow reaction. Okay, when the tertiary carbocation which is treating with the iodide ion, that case it forms the tertiary butyl iodide is obtained. So this is the fast reaction. So this reaction which is carried out according to SN1 mechanism. This reaction which can be carried out according to SN1 mechanism, because here the tertiary butyl carbocation which is highly stable. Okay, it is carbocation intermediate is formed, so it can be follows the SN1 mechanism. In case the phenyl methoxy benzene, when it is undergoes the treating with the hydrogen iodide, so that case also it can be forms the alkyl iodide can be obtained, but which can be followed according to the SN2 mechanism. So in this case the the cleavage which can be takes place between O and CH3 group, the cleavage can be takes place, because benzene ring which is consisting the hyd oxide means oxide ion, so this is having the negative charge, so it has a double bond character. So due to that the cleavage which can be takes place between oxygen and the methyl group. Okay, and here the oxygen and the phenyl group, the cleavage cannot be took place. Here the oxygen and the methyl group, so between that the cleavage can be takes place. This is about the cleavage between carbon and oxygen bond. Okay, next second type of reactions of the ethers, that is electrophilic substitution reactions. So in case of this electrophilic substitution reactions, the aromatic group above that which is having the alkoxy group. So the alkoxy group which is consisting the oxygen has a pair of electron, it can be delocalized towards the ring. So as a result oxygen gets the positive charge and there is a double bond takes place between the first carbon and the oxygen of the alkoxy group, and the negative charge which can be observed on the ortho position. So now the delocalization takes place. So here the different kind of resonance structures can be obtained. So due to these resonance which can be undergoes the electrophilic substitution reaction, and the carbon consisting the benzene ring which are those are getting the negative charges, so that electrophile can be easily attacks on the benzene ring. So in the electrophilic substitution reactions, first one is the nitration. So when the anisole, that is benzene ring which is consisting the methoxy group, that is known as the anisole, or it is also known as methoxybenzene. Now when the anisole which is treating with the nitrate mixture, that is the concentrated nitric acid and concentrated sulfuric acid, so that case which can be obtained the nitro group on the ortho position as well as the para position, that is 1-methoxy 2-nitrobenzene, or also another compound, that is 1-methoxy 4-nitrobenzene. So these are obtained in the case of the nitration. In the case of the bromination, when the anisole which is treating with the bromine, Br2, in the presence of acetic acid, so that case it can be lose the hydrogen bromide and forms the bromine which is at the ortho position as well as the para position, that is 1-bromo 2-methoxybenzene, at the same time which also forms 1-bromo 4-methoxybenzene. So these are the nitration and bromination, and it can also undergoes the two more reactions, that is the Friedel-Crafts alkylation as well as the Friedel-Crafts acylation reaction. So in the Friedel-Crafts alkylation reaction, when the anisole which is treating with the alkyl halide, that is methyl chloride in presence of anhydrous aluminium chloride, so that case it forms the 1-methoxy 2-methylbenzene, it is also known as orthomethoxytoluene, and the other compound also obtained, that is 1-methoxy 4-methylbenzene, it is known as the paramethoxytoluene. So this product can be obtained. Next the Friedel-Crafts acylation. So in the case of the acylation, when the anisole which is treating with the acyl halide in presence of the anhydrous aluminium chloride, so that case it forms the orthomethoxyacetophenone and paramethoxyacetophenone. Two products can be obtained. The orthomethoxyacetophenone which is also known as 1-2-methoxyphenyl ethane 1-one. This is the IUPAC name. Whereas for the paramethoxyacetophenone which is also known as 1-4-methoxyphenyl ethane 1-one. So this is the IUPAC name of these compounds. These are the chemical properties of the ethers. Thank you.